Okay, so in the centralized live media stack, a broadcaster, records their stream using a camera, phone, webcam. They send it to a media server, which basically takes care of doing encoding, transcoding, we'll get into that. And then the output of the encoded stream is sent from a media server onto a CDN. And then finally, consumers watch the stream using a player. And we know that Swarm is meant to be a content delivery network, and it does a great job at it for kind of static or on-demand content. We talk about extending it for live content. But these other layers, kind of the decentralized media server and the decentralized player, don't necessarily exist in the Web3 stack yet. So we'll talk about what we built in Swarm in a second. I just want to spend a little time on the media server to understand what it is and why it's important. So a media server has a lot of jobs. First of all, it's the interface to the rest of the video world. All these cameras, all the hardware encoders that they use, they all kind of speak different formats, codecs, and protocols. So what you need is a media server that can be the input interface for any sort of video stream. And it's also the serving layer, where when you serve video, if someone just requests a file and you just start dumping them the entire file, that's not necessarily the most efficient way to serve video. Some protocols specify creating a manifest of different bit rates so that a player knows what bit rate to request based on their connection speed. Some of them specify playlists of different chunks, which are multi-second segments of video. And the players basically request the chunks one at a time, can buffer them, can switch bit rates as necessary. So again, it's kind of the input and the output layer. But kind of the hardest, the CPU-intensive stuff, is what happens in the middle. It's this transcoding, transrating, transmuxing. And that's taking, transcoding is dealing with codecs. It's taking an input video over MP4 or VP8, like in WebRTC, converting it into H.264, which is probably the most popular codec to date. And this is pretty CPU-intensive process. You also need to do that for audio, even within a video stream. So you maybe go from Opus to AAC or other audio codecs as well. Transrating, that's converting it into all the bit rates, so the video can work at different connection speeds. So someone on a slow cellular connection can watch, say, like a 240p video, even though you're broadcasting in 1080p HD. And transmuxing is finally packaging it into kind of the output transport protocols. And there's lots of different formats of those as well. So just to kind of jump out of the presentation for a second and just give you a taste of how much is going on. If you look at all the codecs that are supported by FFmpeg, it's like a list of hundreds, video, audio, lossless, lossy, et cetera. And the whole existing video ecosystem uses different varieties here. Same thing with formats. So these are the HLS, RTMP output muxes. So you kind of need a media server if you want to work with the existing ecosystem and the outside world. Finally, it provides extra features like DVR, recording, closed captioning, analytics, compositing, so that's taking two streams and combining them together into one for side-by-side or picture-in-picture. So most media servers are totally proprietary. The business model has always been, take a new format, the people that work on it do an implementation, then they license it or get bought by Google to power their web conferencing software, and there's never been an incentive for this to see the light of day. So what we need, if we want to decentralize this and distribute a media server on all the nodes in the network, we kind of need an open version with incentives for people to contribute back all these formats and properties. So any questions about media servers before I get into Swarm? No? Cool. Okay, so Swarm is an awesome CDN for static content. And as we heard yesterday, Swarm has long-lived connections. There's kind of this static topology that's created through the Kademlia. And so we wanted to try extending this to support streams. So we introduced a couple concepts. The first is the idea of a stream ID. How do you identify a stream? And there's really two portions. There's the eNode ID, which identifies kind of the origin broadcaster. And then there's the unique stream ID that identifies that stream. And basically, you concatenate them together to create one stream. And that allows you to use the Kademlia routing to find the origin node who's originating the broadcast. I'm excited to learn about PSS this week because right now we're kind of revealing who the origin node is, which is not great for privacy. But I think with PSS, you could maybe only search for the origin by the first couple bits and get into the right neighborhood of the origin broadcaster without necessarily needing to reveal who's launching this stream, which is probably good for censorship and full decentralization. Okay, so we need messages that support streams. So we extended the buzz protocol. We added a request message, a stop stream message, and messages to request transcoding from the media servers and acknowledge transcoding. And then there's also a stream data message I didn't include here. And we added a new type. So we're not using 4KB chunks like in Swarm because we actually don't need to persist the chunks as they're being transported. Instead, these are time-sliced chunks that right now correspond to HLS video segments. But you can still use the Swarm layer of abstraction underneath. If you want to write these chunks to storage, then you'll persist them as 4KB chunks into Swarm regardless. But the video chunk is kind of the transport envelope. Finally, our kind of routing mechanism is that we added a stream DB so that any node can keep track of its downstream requesting peers. And we added a streamer, which is the interface to the Livepeer media server. So as chunks come in, you can just feed them into the streamer. The streamer will take care of interfacing with the media server that will know how to take these kind of raw payloads, and depending on the type of video, HLS, RTMP, VP8, whatever, it will know how to basically recompose them back into a stream to do appropriate buffering and deal with all the codec stuff under the hood. So the kind of routing model is if you want to watch a stream, you'll make a subscribe request towards the origin. Any intermediate node who receives that request will just store you as a downstream peer. They will make a subscribe request back towards the origin. And then the origin has the video chunks. So they look at their downstream subscribers, which are the intermediate relay nodes. They send them the video, and then those subscribers look at who their downstream subscribers are and pass the video along. So you basically have channels that are flowing from origin to subscriber through Swarm. And that works, as we saw, kind of. It works, but for live video with low latency, you have pretty significant performance requirements. So that's where we'll talk where we go from here.